everyone. My name is Xilinx, and now we will discuss a little bit about UART communication and functional block diagram of FPGA program. And here we can see there is only one module, the red one, which is called top module. And this RXD, it's a wire. Think of the wire sending as a signal, changing bits, zeros and ones based on what's coming in. And we will be using a FPGA clock and Basys board has a clock of 100 megahertz. Then we have a reset button to clear all the input values. And you have a receiver module which uses 10 bits and also uses UART communication, starting bit and 8 data bits and one stop bit. So this RX data which we will get at the output is nothing but the LED is glowing in the FPGA Basys board. So in FPGA board, we get the ASCII values of the input characters. We will get the output in ASCII value in binary 8-bit number. So we will get whatever we'll press on the keyboard, and we will get into a little bit into the theory now. Now, UART communication, basically we are missing on the basis 3. Baud rate is nothing but the rate of data receiving or the rate of which is 9600 bps. Baud rate is simply rate of data transmitting. So basically this UART communication is between the basis 3 mode and the computer terminal. When the keyprobe on the keyboard from the computer is pressed, the 8 bits will be transferred from the keyboard to FPGA through USB-UART port on basis 3 board. 8 LEDs on basis 3 will be used to show the binary value of the ASCII character. All receiving is triggered when a key is pressed on the keyboard. There is a button to reset the output in the LED as well. And we can also turn this into a state machine, a melee machine. Basically, it has two states, that is ideal, and one state is a receiving state. So ideal state is nothing but it's ideal. It's not receiving any data, and receiving state is nothing but the RXD input. We get this the data into this receiving state, and we use some signals. So that is shift signal to show shifting data is ready, and clear bit counter, signal to clear the bit counter, and increment bit counter, signal to increment bit counter, and INC sample computer. It is nothing but signal to increment sample counter, clear sample counter, signal to clear sample counter. So if you look at the timing diagram here, it's basically it's basically at 1. So we can see this is called start here, and we can see the start bit. Basically, when it goes from 1 to 0, it tells that okay, I'm ready to receive the data. After that, we can see 8-bit from here we can see the 8-bit data bits will coming, and after the data are coming, and we can see at the stop here that is the stop 1B1. So the start bit has 1B0 and the stop bit has 1B1. This is the indication that okay, I got the 8 bits enough 8 bits in my data. So for a proper communication, we need a synchronized modules. So here we can see the expected bit correct, which is the 1. Now bit 7 is 1 and the bit 8 is 0, and then we have a stop command. But if we are not synchronized, the bit 8 will think as it got it 1, and then we'll think that okay, next should be stop. But that's when the problem comes. This is the case of which is not synchronized case. So now there is a case called a glitch. Okay, when we from start, when it gets to 0, it needs to able to maintain its 0 state for 100 milliseconds. But if we get the glitch here, that's why we have used the 9600 baud rate, which helps in the start bit be detected, so that it remains at 0 for a 100 milliseconds time period. And next thing is this sampling of middle data bits. Now for the UART communication, we use first basically an 8 clock cycles, and then we get 16 clock cycles, and every we have a mid bit for every start bit, and for every data bit we check at the mid bit of the sampling data. Now we will get into the some basic terminologies. Asynchronous UART communication does not share a clock between sender and receiver, requiring synchronization. And the receiver detects the start bit to begin sampling the incomplete data. And oversampling is to increase timing accuracy and correctly locate the middle of each bit. So after detecting the start bit, the receiver counts to 8 in 16x oversampling to find the center of the bit for sampling. Then we have some UART samples every 16 counts to read the rest of the data bits accurately. Higher oversampling rates like 32x offer better accuracy but consume more power and require faster clocks. And the baud rate, and once again, so I will summarize about baud rate is speed at which data is transmitted. So for this, we have taken 9600, and the counter transmit data sequentially at the baud rate and synchronized with each baud pulse. The receiver circuitry watches the RX line. So for consecutive low signals to detect the start bit and then shifts in data accordingly. And the system clock counters are reset with each baud pulse to preview. Now I will explain about the Verilog code which I used to create a communication between my computer laptop keyboard and the FPGA basic keyboard. Now I'll explain about the code that I have written here. So basically, the input clock FPGA is nothing but the 100, which is a 100 megahertz FPGA clock, and this is the reset button, and this I have taken as the input serial input lines, and this RX data that we received at the receiving end using 8-bit, most LEDs will be on. Now this is the internal variables that I have taken. This red shift is nothing but the triggering the shifting of data, and the state and next state is the initial state and the next variable state. And this 4-bit counter is the total length of the bit is 10, 1 bit byte of data, and this 2-bit sample counter is the frequency. We have to take 4 times the baud rate. For this, I've taken the sample counter, and this 14-bit baud rate counter is for setting up a baud rate of 9600, and this 10-bit RX register shift is data byte 10 bits, that is 9 bits data byte, and this clear bit counter and increment bit counter is to clear and increment the bit counter and sample counter. And let us talk about the constants that I have taken now. So the parameters, I already explained earlier that you should decode the 100 megahertz and the baud rate should be 9600. The sample should be 4 because we are taking the frequency as the 4 times the baud rate. And this parameter div counter is nothing but this is the frequency we have to divide the system clock to get a frequency div sample time higher than the baud rate. And the div bit we have taken the 10. This bit sample, this is the midpoint of a bit where you want to sample the data. This 10-bit div bit you have to get the idea because earlier the state diagram I have shown that start, stop, and 8 bits of data. Then this 10 div bit is nothing but the 1 bit, 1 stop, and 8 bits of data. Now this statement nothing but ascending the RX data from the shift register. Now let us understand the receiver timing logic. So if reset gets to if reset button is pressed and all the counters are reset, then if then this is ideal. The sample rate and everything gets to the same state, and or else then if baud rate this statement if the counter reaches the baud rate with sampling, then baud rate will be the reset counter and state the state in this line. It should be ready to receive the data and switch to receiving state. And this line is nothing but if shift is asserted, then load the receiving data. If this statement is asserted, then reset the sample counter. If the increment is asserted, then it will be incremented by 1. And this clear bit, if this clear bit if is asserted, should be reset itself. And lastly, about this bit counter, it will be goes up by 1 if this statement gets executed. Now I will explain about the UART receiver state machine. This is nothing but the trigger by always either it was like nothing but trigger by clock, and the shift is nothing but set shift to 0 to avoid any shifting, and this is an ideal state. Now let us get into this case state. If then if we look at this RxD, if input RxD is asserted, then we will begin the state this state will be the ideal state and next state in the ideal state. And this clear counter will all be, or else if it is not done, this clear count, this else begin next state, it will be the same state. And this clear counter trigger clear the bit counter, and this clear sample counter will clear the sample counter. Now we should get into this case one, receiving state. This state, it's already is a default remaining receiving, and this line which is nothing but if the sample counter is 1, it triggers shift. If this statement is nothing but the sample counter is counter as 3 and the sample rate is used is 4. And if we look at this statement, it's nothing but this statement trigger the increment if the bit counter is not 9, and it clear this nothing but clear the sample counter to reset the sample counter, trigger the sample counter to reset the sample counter, or else then if the sample counter is not 4 or not equal to 3, that means 0 to 3, then in this case, and the default state will be idle state, and the next step should be default fail back to ideal. So this is the code that I have written for the communication between the keyboard and FPGA Basys board, and I have to run simulation and synthesis and implementation and generate bit stream. I have skip this part because this is a time-taking process, and I will directly get into the hardware. How it's the how how if I type any command, any character in the keyboard, how the LEDs are glowing in the FPGA board. I will get into the video hardware video right now. And as one thing, if and for proper serial communication between the keyboard and the FPGA board, we need to download this Terraterm file. If you open this Terraterm file, we get to connect this serial, and we have to choose the USB port you have to use. After that, if we press anything, we will get the binary value, binary ASCII value in the keyboard. Let's get into the hardware part, right?
So now we program the code, dump the code into the hardware Basys 3 board. So if I press R, now I get this 8-bit binary value of R. The 8-bit binary value for R is its X number is 72. Its binary number is 1110 0010, which is correct. And also I can do for A ASCII value is X number is 61. So for 61 X number, the binary number will be 11000001, which is also correct. So we can now I can type any character, I get its ASCII value in 8-bit binary number. So this is my project.